My name is Dave Cadu. I'm honored to be your CEO and director of IWCS, and I'll be your moderator for today's webinar. A few housekeeping items for you. Please note that as an attendee, you're part of a larger audience. So during the presentation, all participants will remain in listen-only mode. Also, as a reminder, this event is being recorded for rebroadcast through our website. We encourage you to submit any questions that you have at any time during the presentations. During the presentation, your questions will be written using the chat panel on the right of your screen. So open up the chat panel, and after typing your questions in the space at the bottom, please be sure to hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. Also, I want to remind you, as I mentioned, we're all getting very excited to prepare and create the program for the September conference in Orlando. All of you are invited to kindly consider creating a technical paper and submitting your abstract. The call for papers is now open. And we also have a prize if you refer a colleague and that colleague mentions you in the abstract submittal process. You have an opportunity to win a free registration to the conference. So we hope you'll take advantage of that. And as you'll see now, you'll see one of the most excellent presentations that we had in the 2022 conference. And you too can also be like Paul and submit a paper yourself. So with that, today we welcome Paul Brigandy. Paul is the application technology leader for Dow in Pennsylvania, USA. Paul will be presenting his paper on a sustainable approach for polyethylene cable jacket compounds. Dr. Paul Brigandy is application technology leader for Dow Packaging and specialty plastics wire and cable business in North America, based in Collegeville, Pennsylvania. Paul has experience in the power transmission and distribution, as well as telecommunications markets, focused on research and development of new insulation, jacket, conductive composites, and polymer modifier material developments. His technical expertise includes formulation and processing of polyolefins, elastomers, and polymer composites. Paul is active in several industry organizations, including the Insulated Conductors Committee, the Communications Cable and Connectivity Association, Fiber Broadband Association. He is also the first vice president and on the board of directors of the Society of Plastics Engineers in the Mid-Atlantic section. Paul earned a doctorate degree in polymer science and engineering from Lehigh University and a Bachelor of Science in chemical engineering from the University of Delaware. He is also an active adjunct professor at Lehigh in the material science and engineering department. So Paul, we welcome you and thank you for being with us today, and look forward to your presentation.
Great, thank you, Dave. Hopefully everybody can see the slides and hear me well. So today, I'm glad to be here on behalf of kind of the broader Dow team, those listed and handful of others behind the scenes that helped with this work. So yeah, today, as Dave mentioned, what we wanted to do was talk a little bit about sustainable approaches when we consider things like our polyethylene jacketing materials that are used across the industry. So just as we look at the outline and kind of walk through, I'll go through in a little bit of an introduction, and we'll look at some of the sustainability drivers and the approaches that are out there today. In particular, we're going to talk about mechanical recycling and post-consumer recycled plastic materials. That will be the focus of today's talk. And we'll go through some experimental studies that we did, and we'll share some of those results where we looked at incorporating the mechanical recycled plastic into jacketing type compositions. And then we'll go through just a quick summary. So one of the biggest drivers right now, and for those based in North America or following the North America market, right, is a lot of the investment with respect to the infrastructure and the bill that was passed in 2021, where greater than $500 billion are going to go into the infrastructure improvement program. And, a lot of that has to do with the wire and cable industry. So over about $65 billion just with respect to broadband. So a huge investment, and with that comes huge opportunity, right? As we look at this huge investment and how can we move the industry to support the industry to be able to deploy all of this cable, but also thinking about where we're headed in the future and making sure that we're doing it as sustainably as we can, with as low a carbon footprint as we can, and doing our part as an industry. So as I said, this sustainability, right, is really going to impacts all of us across industry. So, we'll talk about wire and cable today, but you see the majority of this in the packaging space or the consumer space, where sustainability's really been pushed from a single-use packaging type of applications. We've all seen things around plastic waste, and so those are really the drivers for it. But again, we all kind of have a part in this as we look into the more durable goods, right? So things like cable, where they are really meant to be long-lasting, highly efficient, and they are sustainable in that way. But how can we also take it a step further? And that's what we'll kind of talk about as we go through the presentation on other concepts that we can look at to further improve that. And whether it's the North American CHIPS Act, the climate bill, the combination for things made in America preferred in some applications, there is this strong demand for driving the infrastructure improvements, but doing it in a sustainable way, where these solutions are not only long-term, but also kind of from the start, taking that all into account. So when we hear sustainability, I think it is a broad term, and there are many ways that a company, a person even, can approach being more sustainable in what they do. This is just kind of a high-level look at a little bit of how we're looking at it, and some of the buckets that we're focused on across our portfolio, with things like safer materials, right? So I think things in that regard, you can include maybe halogen-free type of applications for flame retardants, as well as other types of materials. But really looking at the safe aspect of the material as far as substances of concern, and there's a lot of things that can go into that bucket. I think overall we're all looking for reductions in carbon emissions. I think that is a major driver. And there's, again, a whole host of things that can kind of fall into that bucket, which we won't go through today, as well as renewable feedstock. So renewable, bio-based kind of activity in the polymer world is out there, as well as advanced recycling, taking end-of-life plastic and turning it back into the building blocks. we won't talk about those either. I think what we're going to focus on today is this mechanical recycling. So you'll see this a lot in consumer and packaging applications today. Things like just your water bottle, a single-use water bottle, or reusable water bottle, I should say. That's where we're really going to focus our conversation, and how can we look at incorporating that, whether it be recycled, say polyethylenes from other uses, or even potentially bringing, back around any cable material. So for anybody that's not really familiar or hasn't heard the terms before, what is mechanical recycling? What is PCR, or post-consumer recycled plastic? Basically what it is collected, right? Used plastics will be collected and sorted, and then moved into another process where the waste is processed to produce basically a secondary raw material, or this is post-consumer recycled resin, right? So it can be anything from taking the material, grinding it, and ending up with some flake material, or you can often find various sources where some of it is actually kind of like a pelletized material that's a little bit more easy to use. But then ultimately these resins are then used to produce new goods, right? So again, whether it's in the packaging space for shrink wrap on water bottles, or what we'll talk about today is really the cables, and in particular, and just focusing in on the jacket as a proof of concept on where we could take it. But there are other applications within the cable world, obviously, that we could also look at. But it's really advancing the circularity of this plastic and giving it another life in use, right? So trying to promote the circularity. So what are some of the options for mechanical recycling in wire and cable? Well, we can formulate with it, right? We can include it into compounds such as jacketing. In this case, right, so going into more of an industrial space, we could look at post-consumer recycled materials, but also this PIR, right, so post-industrial recycled content. So there's various sources that we can look at and try to utilize in the most efficient way possible, while keeping kind of the full supply chain and carbon footprint in view. And then we can look at this for other applications, right? As I said, jacketing is one, but there could be other portions of the cable, or the other parts of kind of the cable supply chain where we could look at it and just really utilize the full breadth of a polymer toolbox. So what we're going to talk about today is a few case studies where we looked at incorporating these different types of resins into the jacket. But I list a few other applications where things could be looked at, particularly from a communication standpoint, but by no means is it limited. Okay, so kind of moving into what we did and how we looked at this from a high-level approach. We basically started with some virgin polymer, traditional material that you would use in applications today. So we have a medium density based polymer and a high density based polymer, just with the basic properties listed. But then we took what I'm showing here is basically a natural high density PCR resin, which was more or less in the form of pellets, as I mentioned before. But then also, what you might consider this worst case scenario as far as quality of PCR, where it's colored high density based flakes, right? So you can see kind of the form, how random it is, the types of material that's in there, and colors, right? So in some applications that won't be very useful, but here we're just taking it into an application where it's black. So we did include that as a kind of a worst case on this one, and then maybe a more pure type natural. So we covered our breadth there. What we kind of looked at were really just trying to look at selected properties for jacket compounds, really just to kind of get a feel for how these materials would work, what kind of baseline information we could generate in jacket compounds. So we did make we took the resin, the other components, and the PCR, and we did incorporate them into one single jacket compound. Looking at things like density, melt index, tensile strength, and elongation. These are just some of the targeted properties and specifications that we would look to meet. But we did do some other testing, which I'll show, more of the longer environmental type tests. So the first case study we'll look at is really we started with a medium density base, just from the standpoint of a lot of the applications today in North America anyway. And we looked at the medium density type jacket with both the natural and the mixed colored PCR resins. Okay, so what you'll see is, right, we have a control medium density jacket where there's no PCR in it. And you can see kind of the melt index and density there. And then we looked at the medium density base polymer plus natural PCR or colored, varying that PCR weight percent from 10 to 100, which would be all of the PCR, but formulated into the jacket compound. And what you can see is kind of the range of somewhat the melt index, as dictated a little bit by how much PCR was there, as well as the density, right? So there is some fluctuation as far as those properties, and really it's driven by the amount and the type of PCR. Again, kind of looking at this from a worst case scenario, and in the fact that the PCR was high density and somewhat not controlled, right? So that's, though the densities are a bit higher, we were kind of paring this down with a medium density base in this case. If you look to the right-hand side, what this shows is you actually have very good processability across the materials. So we've got the control all the way up to 100% is in here. It's just cut off on the legend, but you can see very, very similar viscosity versus shear rate curves in a parallel plate type rheometer. So from the standpoint of flow and processability, the materials behaved well and very similar to the controls as we would expect. The mechanical properties are really where you start to see some of the different deviations when you talk about the PCR materials and the randomness of the type of material that you get. So you can see the control kind of to the left-hand side with very good tensile and elongation properties. But as you go higher and higher in PCR content, mainly what you see fall off, the biggest drop is really in the 50 to 100% on the natural PCR, but definitely at the 100%. So, definitely see up to 50% is fairly good. 25 to 50 could work, if optimized. But then in here where you look at the colored, right, again, when we kind of consider worst case based on how different the sources could be, you see the drop off pretty dramatically, particularly in the 100% itself. So again, but with good performance up to about the 25%, which is, in many cases where, you might see PCR even in other applications, kind of that loading is considered acceptable and useful from a sustainability point of view. So along with the mechanical properties, another critical thing that we looked at was the environmental stress crack resistance. So when you consider the colored and the natural PCRs against the control, where the control can last greater than 4,000 hours, what you see, particularly at, again, the higher percentages of PCR itself, you have much lower stress crack resistance, so less than 24 hours for the pure PCR. But as you incorporate around 25 to 50%, depending on depending on the source, you can start to get better performance, and it really would depend on, in this case, we say, kind of up to 25, again, 50 maybe, depending on the specification or targets for a given application. This you could find some applicability with PCR loaded at those amounts. I think one thing that's interesting and kind of hypothesized around the colored in terms of performance, right? I think here you actually have more of a variety of polymer material and different sources, different molecular weights, distributions, things like that, you actually see a little bit better ESCR on the colored in this case versus the natural, whereas the previous we saw the opposite. So one last thing we did was put these compounds onto a wire using our pilot size extruder, so 2.5-inch extrusion line, where we looked then at the surface roughness, so taking the wire, putting it through a profilometer. And what you can see here is actually very good performance across the board relative to the variety of compounds. Again, even the colored. So in general, from a smoothness standpoint, we look at roughly around 20 microinch as being a very smooth wire. So in this case, all of them, including the PCR, contain 100% PCR samples, were pretty good processing materials. And again, I think when you look at the 100%, it kind of plays into the variety of types of polymers that you have, which lends itself to better processability, or at least good enough processability. All right, so the last thing we'll talk about now is just looking at medium density and high density blends. So I showed the types of polymers to begin with, but some of the more higher performance polymers and blending them with, in this case, what we consider just the mixed color PCR as, again, the worst case scenario based on the polymers of choice. So again, here we have medium density and high density as the basis, blended with, so now we would add in anywhere from 0 again to 100%. So 100% will be the same as before when we consider the color, but included it for reference. And again, melt index and density, again, noting that in this case, the densities of the compounds are higher just because of the starting source of PCR that was available to us. Obviously, there's other sources, and we can tailor or optimize based on targeted densities. But again, here we want to show the kind of the viscosity versus the shear rate. Viscosity on the left axis, shear rate on the Y in a parallel plate. And you see very good shear thinning behavior, particularly at the high shear rates, a little bit of deviation at the lower shear rates. But again, it in this case appears to be maybe a little bit driven by the variation in the PCR component that we have relative to the resin on the various structures of the starting polymers in the MDP and the HDP. On the HDP side, a lot closer in terms of the rheology. Here again, we show the mechanical properties. Again, you can really reach a nice balance of properties with the enhanced resins. Here again, it depends on you know, how much you'd be wanting to target to kind of claim recycled content in a cable. But also looking here again at a worst case scenario with these, it looks we would say right about 25 again to upwards of 50 based on optimization, right? So there is opportunity to fall into this range based on type of polymer and type of PCR used. But just gives you kind of a flavor for how the materials will perform at varying levels of recycled content. And again, similar trend, you see the drop off as you increase the amount of recycled content. Similarly with ESCR, again, depending on kind of the applications or targets that you would have, there is a range that you can get of performance, but really I would say kind of in that 25 to 50% range. With these higher performance resins, you can have a fairly good, relatively good stress crack resistance, as you can see upwards of 1,000 hours or more, with 25% in high density, which tends to have a bit lower ESCR depending on the material. That medium density even over 2,000 hours now in this case with the higher performance starting resins, where 50% loading gets you that 2,000, and then even lower you can still meet reach the 4,000 hours. And lastly, similar, we have the smoothness. So we looked again at the extrusion performance and the final wire or cable surface smoothness. And again, looking for less than about 20. In this case, again, all of them were very good as far as being able to produce a cable with a smooth surface at what I mean. Typical polyethylene jacket processing conditions. Nothing special about how the materials were processed. Basically, a drop into a standard processing condition and setup. So with that, hopefully we left you with the notion that really sustainability is a significant market driver. And that's not just North America, but globally. There are increasing pressures to be more sustainable across industries, not just wire and cable, and it's not just a packaging challenge. It's an industry and it's a global challenge that we all can look at different ways to promote and produce more sustainable solutions. And it's not one, there's no one answer, but here hopefully what we've been able to do is show that there is some feasibility in incorporating these post-consumer recycled materials into different polymers and take advantage of them and look at different sources, content, application targets that we really want to have conversations on and be able to collaborate to come up with the best overall sustainable solution. Again, I think one of the questions that was asked relative in the presentation before at the conference, I think it really isn't just a materials issue. It's kind of looking at it from start to finish, supply chain included, and how do we collect it? How do we process it? How do we transport it around? That has a big impact on what we do or how it impacts the overall footprint. So it is really a combination of all those things together. But this is just one way to think about potentially whether it be, we would love to work on coming up with these solutions. So whether it be incorporating 20 to 50% PCR and achieving what we found was reasonable jacket performance when we look at both traditional resins, but also as we look at enhanced resins, being able to maximize the amount of recycled content that we could potentially introduce by even just taking advantage of enhanced properties within today's polymers. And alternatively, looking at low levels of these enhanced polymers to really boost the performance of PCR. Again, whether it's maybe not in those cases jacketing, but maybe up jacketing or strength components or filler components. I think there's totally an open end of opportunities that we can look at for things like this. So with that, I will leave my contact information and be happy to take any questions.
Well, thank you, Paul. Again, as we were when we were together in Providence, an excellent presentation. And looking at the questions that we've received, clearly this is a topic of great interest globally. So we thank you for your time this morning to present this important subject. So let me get into a couple of the questions here. And again, I'll remind the audience that if you do have any questions for Paul, please enter them in the chat function on the right of your screen, type them and then hit send, and we'll try to get to them. So Paul, since wire and cable extrusion process is very susceptible to molecular weight and molecular weight distribution changes, what are your thoughts on impact of PCR or mechanically recycled materials on processability and production rates?
Yeah, so that's a good question, and I think at least what we found based on, I'll go back here, right? When we look at the extrusion overall, but also I'll just take this as an example, looking at the colored. I think you actually find that they can tend to be beneficial in the sense that you end up with a bit more of a broad distribution. Again, because of the different range of recycled materials that end up in it, that actually lends to the higher speed, more extrusion processing friendly type of material, as to opposed with something that's more narrow, which tend to be a bit tougher to get higher speeds and good smoothness on the surface. These actually tend to seem like they would trend in the right direction to help kind of boost that relative to something that's more narrow.
Very good. All right, thank you. What is the key chain structure difference between medium density and high density? Is medium density close to low density?
So yeah, I think the answer maybe can take it. I can certainly provide more offline, but in short, right? Yeah, low density, medium density, high density. Really, the difference in the structure is going to be the amount of branching that you see in the polyethylene backbone or off the polyethylene backbone. With low density having much more branching, high density having much less, which really drives how crystalline the material will be.
Good. And with that reminder, you can reach out to Paul directly, either through this link here, or you'll see his phone contacts in just a minute. What is your ESCR target? Have you considered alternate tests for stress crack resistance in contaminated materials like UCLS? Do you have an expected lifetime average service temperature for these cables that relates to ESCR?
That's a good question. I mean, no, we don't. We didn't have anything specific in in target here, right? I mean, in general, I think we see very different regional needs. I think what clearly the 4,000 hours or 2,000 hours even can be one of the more stringent lengths of time. We also see shorter. So in this case, we were really trying to get a baseline for where the materials would perform relative to, as you saw, control samples, right, which were much longer in ESCR. So I think it's a conversation we'd want to have on what are the needs of a particular region or a particular application. But I think what, at least what the data shows, is there are opportunities to still incorporate this recycled material and meet even the longer, more stringent ESCR. We haven't really looked at other ESCR or stress crack methods. Kind of just based it off here on the standard one.
Okay. Could acceptable performance with greater than 50% PCR be possible through the use of additives or modifiers? They're thinking about tensile properties, stress crack resistance, impact resistance, things like that. Are there any modifiers that help improve?
Yeah, I mean, absolutely. I think that's something that could be looked at. It wasn't here. And so I think that's, again, kind of a conversation we'd want to have, is really where do you want to go, right? What are the targets that you need to meet, or you know, as to how much we could incorporate, and then what might have to be introduced to be able to meet that. But absolutely, modifiers or, you know, different polymer materials to couple or combine would certainly be something that could be considered here.
Yeah. Not a modifier, but what does adding flame retardants do to the various properties?
Yeah, that's another great question. I think a similar one at the conference. It isn't something we looked at here. I think obviously you could potentially do that in a similar way, and adding the recycled materials to a new compound. Now, I think one of the things you would probably need to be careful of is if you're talking about trying to recycle flame retardant materials, you're obviously then diluting them. So you would have to just kind of take that into account. But it's a good question, just not something that we've gotten to as far as that far down on applications yet.
Okay. I guess we all assume that material can only be recycled a certain number of times before you lose enough plasticizer and properties for it to be viable. Is this true?
I think it depends. I think you do see differences as materials are processed. I don't really have a number as far as, you know, what that is, but yeah, I think the properties will deteriorate the more you process them. So again, really one of the reasons you just have to be careful about the sources you bring in, and, you know, really making sure you have the right methods of quality control in place to make sure that things are acceptable for particular applications. I think obviously we'd be more concerned about it for us maybe in this industry versus you know, a plastic trash bag or something. But, you know, it really is something that would have to be considered.
Right. Have you or any cable suppliers that you know of tried to evaluate this PCR material as an insulation? And if so, what applications and how would it affect electrical performance?
Don't know that I could speak for anybody else, but from our side, we haven't really moved to the insulation space. I think it's something that could be looked at. I would expect just given the variety of materials, additives, quality to begin with, multiple handlings, that it may be more challenging than some of the other potential areas of use.
Yeah.
But we haven't looked at it at this point.
Fair enough. Yeah, insulation, there's a lot of other things to be considered as well. How do you mix and guarantee the stability and final properties of the material in production?
So I mean, I would say, yeah, we would use similar mixing technologies that we use today for the, the jacketing compounds. I think, again, the key would be to make sure that you have, as I would say, as consistent a supply as you can on the PCR side. Obviously, you'd have to look at your quality control measures that may or may not be the same as a traditional material. I think most likely they'd be more or less the same. Maybe we could do something more, but I think that's, I mean, in our case, what we've tried to do, and just kind of speaking from a high level, is there are agreements in place to have certain supplies of PCR that would come in that we would utilize, versus trying to, just use too many different random sources. And I mean, that's just something that's being done today in the packaging side, where we would look to kind of leverage what's being done from a broader view.
Just a few more questions. Are these materials offered by Dow, or do manufacturers mix them with their own sources? You talked about the importance of sourcing.
Yeah, I would. I mean, I guess the best thing I would say is reach out. I think there's multiple ways that things can be achieved. But so I would say we are looking at providing compounds to the marketplace, but happy to have those conversations.
Great. For the jacket extrusion process, what's the maximum PCR post-consumer recycled polyethylene that you recommend? I assume that's looking for like a percentage.
That we'd recommend, yeah, the only thing I could say is, if you're just strictly looking at the extrusion, as I said, I mean, the data here, right, showed that pretty much, that's right here, right? Like, so even if you just look at the last slide, just from a processing standpoint and getting a smooth surface on the cable, I mean, you could just process some of these PCRs alone, right? And actually make a smooth cable. Where you need to concern yourself is everything else, right? So you have to find the right optimal balance if you're concerned about any of the other properties. If you're just looking at extrusion, I mean, you could theoretically look at 100%.
Okay. Two more questions. Which are the base characteristics that you might suggest to control recycle mechanical polyethylene before blending with virgin grade? I mean, is there a characteristic that you might measure and then address the amount?
I think, right, I mean, in a similar fashion, right, I think things that we see are typical polymer properties, something like a melt index, a density. You're gonna get those numbers from a, let's say, a supplier of PCR. I mean, I think those, and maybe there's some other ones that you could look at, but you're kind of treating it as a polymer. It's just you kind of know that it's various sources. So I think that's the main thing that we've seen. There's probably others. I don't know all of them off the top of my head, though.
Right. And one last question. The long-term aging properties, how might they compare against the virgin materials?
Yeah, so I think that's something else that would need to be considered. In this case, for us, we are these are restabilized, right? So we would add just as we would for traditional materials. So the design on these would be that they would be just as good, right? You're just starting with different materials, but they'd be stabilized such that they can meet the long-term performance that would be expected.
Very good. So with that, again, great questions, and we thank everyone in the audience for your participation. Paul, again, we must thank you for this very interesting and important topic that you presented today. Please note the contact points. You had the QR code on the previous slide, but you can see the email address and phone number for Paul, and you can reach out to him after today's event. Each of these IWCS webinar series events are recorded and will be archived on the IWCS.org website. It normally takes some time, a week or two or so, for these to be posted. The IWCS webinar series will conduct technical paper presentation webinars, as well as sponsored company events several times each month. Our next scheduled technical paper presentation webinar will be on Friday, February 17th at 10:30 a.m. Eastern USA time. We typically conduct these on the third Friday of each month. This month was a slight exception, but again, you can bank on a technical presentation each month. Each of you will be receiving an announcement for the event. Please feel free to share those announcements with your colleagues so that they can join and register as well. I do want to remind you again, all of you are invited to please review with your company, and the important work that you are doing will be extremely vital to our industry as a whole. So we would invite you to submit a technical abstract and present a paper at our Cable and Connectivity Industry Forum in September in Orlando, Florida. And if any of you can refer one of your colleagues to present a paper, please ask them to include your name, and you'll be submitted into a drawing for a free registration. So look forward to your help in obtaining the important abstracts for our technical symposium. We must recognize the important partner sponsors for IWCS, including Dow, but each of these sponsors greatly contribute to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, we thank each of these leading suppliers in our industry for your support. So as I mentioned, we're all very excited to be preparing and setting the program for our 2023 conference. It'll be our 72nd annual conference. It'll be September 17th through 20th in Orlando, Florida at the Gaylord Palms Resort and Convention Center, a very attractive destination. And for those of you who haven't been able to get to Orlando, like all of us over the last number of years, maybe now's a good time for you to bring the family and come back and enjoy Orlando. So please watch your inbox, social media, and our website to learn more as information becomes available. So our website is IWCS.org. So thank you for participating today, and this concludes our webinar event. Thanks. Have a great weekend, everyone. Thanks, Paul.
Thank you, everyone.